Today, we are going to dive in to discover geological wonders, the strangest formations, and sometimes monumental structures hidden at the bottom of our planet's seas. To understand what lies at the bottom of the oceans, let's begin by imagining them empty.
Here is the world map as we are used to seeing it. Except that 2/3 of its surface are hidden on the other side of the mirror, under the water. And when we remove them, by the power of imagination alone, we gradually see plateaus appear, the extensions of the continents beneath the surface of the oceans, and then the reliefs. Protrusions take shape across all the ocean floors of the world before the immense abyssal plains are revealed. And finally, when almost all the water has been removed, only a few immense cliffs remain at the deepest ocean trenches.
To grasp the vastness of the topography of the revealed abyss, consider that all the land above sea level rises on average about 700 meters, while the average depth of the oceans is more than 3,800 meters. Thus, the ocean floor is far from being that immense, monotonous, and seemingly endless abyssal plain that we usually imagine.
In reality, if you could walk there, chances are you would quickly fall onto steep regions dotted with immense crevasses, countless gorges, rifts, and cliffs. Regions where canyons carve deep into the ocean floor, and others where aborted islands appear. Majestic underwater mountains sometimes rise more than 4,000 meters above the ocean floor.
Because in all the oceans of the world, sometimes just a few hundred or even a few dozen meters below the surface of the waves, you can find mountains. Today, more than 100,000 underwater mountains over 1,000 meters high are known, and it is estimated that the number of those over 100 meters high is nearly 2 million. Just think that the Pacific Ocean alone, with its area of more than 155 million square kilometers, and larger than all the continents combined, contains so many underwater worlds that if they were all gathered in the same place, then their total area would be roughly comparable to that of Europe.
And these combined dimensions, already phenomenal, are a reflection of our ignorance, which is to say immense. At first glance, the ocean floors in these images appear well covered. However, zooming in reveals numerous unknown areas. Only the clearest streaks correspond to areas mapped in detail by research vessels. In reality, the maps of the deep sea that we have today have a resolution of about 1 kilometer over less than 18% of the planet's seafloor surface. To put it another way, we have more detailed maps of the surface of Mars than of our own seafloor, hidden under thousands of meters of water. And if you point an amateur telescope at the moon, many of the small craters you can see there would be completely unknown to us if they were lying at the bottom of the ocean. On Earth.
In many places, the data is inaccurate, and what we think is a homogeneous abyssal plain actually isn't. It often teems with features too small to be visible on our screens. That's why it's not uncommon during expeditions to discover unknown features, underwater mountains that don't even have a name yet, or literally to stumble upon them by accident. Like in 2005 when, during a dive at barely 150 meters deep, an American nuclear attack submarine collided with an underwater mountain in the Gulf of Mexico that was completely missing from its nautical charts.
And the craziest thing about all this is that, among the 100,000 seamounts over 1,000 meters that we've recorded, only 0.1% have been explored. Often, these white peaks of the deep blue are, from the perspective of the marine life that develops there, in total contrast with the relative emptiness of the surrounding ocean floor. Because these formations are refuges that offer corals, sponges, and anemones that cling to them environments where they can thrive.
Here, animals find accessible and concentrated food in much greater abundance than in the surrounding deep waters. Because of their formations, these seamounts act as obstacles that locally disrupt the flow of water, creating turbulence and sometimes significant upwellings of cold water rich in nutrients from deep currents. Thus, it is not uncommon to find explosions of planktonic life at the top of these submerged mountains, attracting the hungry of all sizes. Schools of fish, turtles, sharks, or whales.
And far from these unevenly distributed and often solitary or isolated underwater mountains, there is a structure beneath the waters that contains tens of thousands of them. It's the mid-ocean ridge, which is by far the longest mountain range on our planet. With more than 65,000 kilometers in length and peaks averaging over 3,000 meters high. Above the seafloor, it winds around the globe, forming a gigantic massif that connects the four oceans and covers, pardon me, but that's roughly 23% of Earth's entire surface area.
From this ridge, which we entered for the first time after walking on the moon, about half has been mapped in high resolution and less than 1% has been explored in detail. At the center of this range are deep valleys, on average as deep and wide as the Grand Canyon. It is at this rift that the movement of tectonic plates continuously creates new seafloor, which slowly spreads on either side of the fault zone at a rate of 2 to 5 centimeters per year.
Due to the intense geological forces present, these areas are home to 20,000 fires under the sea. Because this underwater mountain range is far from being a peaceful place for hiking. And many of the mountain ranges found on either side of the rift are volcanoes that occasionally erupt. In fact, 75% of the Earth's volcanic activity is concentrated along this ridge. In other words, 3/4 of the lava produced each year on the surface of our planet flows and forms at the bottom of the seas.
It's estimated that around 20 eruptions are currently occurring at the bottom of the oceans. The Earth's largest volcano is located under the oceans. Known as the Tamu Massif, this giant, located about 1,500 kilometers east of Japan and currently dormant, rises to 4,200 meters above the abyssal plain. It also covers an area larger than that of Great Britain.
Not only are they countless, but the landscapes created by this volcanic activity are often incomparable to those we are used to seeing on land. Because in the great depths, when lava at 1200 degrees breaks through the ocean floor and comes into contact with the water at 2 degrees, there is no explosion, but rather a vitrification of the magma's surface. The thermal conductivity of the water, aided by the pressure, transforms the surface of the cooled rocks into a thin layer of glass, solid but also malleable, with the appearance of stone cushions, the pillow lavas. Over time, as eruptions occur, these cushions flow and pile up. So it's not uncommon, when diving at the same site several years apart, to find that it has gained more than 100 meters in thickness.
But on rare occasions, the autonomous rover's cameras capture a different spectacle. That of an underwater explosion like the one you're seeing on the screen right now, which was filmed in 2014, during an eruption that occurred close enough to the surface for the water to vaporize upon contact with the burning lava, creating an impressive plume of steam filled with microscopic lava debris, carbon dioxide that was initially dissolved in the magma, and sulfur, which is responsible for that strange yellowish tint. And we've even discovered asphalt volcanoes at the bottom of the seas.
When we first encountered these odd structures, we thought they were forgotten paving stones from a ship. Yet, what you're seeing here is indeed the result of an eruption, a very unusual eruption. In the deep sea, volcanism is not always associated with a flow of glowing rocks. Here, after being cooked for thousands of years deep within the crust, the burning oils from a natural hydrocarbon reservoir eventually broke through to the surface of the seafloor, and hot asphalt came into contact with cold seawater. As the volatile components in the thick, viscous hydrocarbon fluid escaped, it hardened and solidified, forming tar lily petals and asphaltic water lilies, sometimes several meters wide.
But now, let's leave these volcanic formations and turn our attention to the trenches and canyons that dot the ocean floor, and which often rival or even surpass in size anything we know on Earth. Actually, to find these features, you don't have to go very far. Just think, off the coast of Cape Breton, there's an underwater canyon that's as large as the American Grand Canyon. Off the coast of mainland France, there's a cliff that's 1,000 kilometers long. And it drops from the continental shelf, 4,000 meters down, all the way to the abyssal plain. And there are countless examples of gigantic structures like this throughout the world's oceans. In the Bering Strait, for example, there's the Shemchung, the largest and deepest underwater canyon on the planet, which is a mandatory passageway for the flow of cold waters coming from the Arctic. The Mona Canyon, located off the coast of Puerto Rico at a depth of 4,000 meters, is 140 kilometers long and 30 kilometers wide.
These pronounced landforms, like those found on Earth, are even the setting for water flow between Brazil and Africa. At the Romanche Trench, at a depth of 7,760 meters, there is a rocky groove that is 300 kilometers long, and on average 19 kilometers wide, which, like a funnel from the depths, connects the western and eastern Atlantic basins, through which deep cold water rushes and circulates, with a flow estimated to be 10 times that of the Amazon.
There are even underwater waterfalls beneath the surface. It's between Iceland and Greenland at the strait known as the Denmark Strait. That's where the largest waterfall in the world is found, carrying about 116 times more water per second than the largest waterfalls on land. These deep water cataracts originate in the icy waters of the Arctic, which, being denser than those coming from the south, flow along the bottom of the strait at a depth of 600 meters, following the shape of a steep cliff before ending their fall at the ocean floor, 2,400 meters below.
Elsewhere, the significant differences in salinity that can exist from one region of the sea to another can lead to the formation of other, equally strange phenomena. In fact, rivers and lakes have been identified beneath the seas. At the bottom of the Bosphorus Strait, connecting the Black Sea to the Mediterranean, an underwater river flows with denser water than its surroundings. And if it were on dry land, it would be the sixth largest river in the world in terms of flow rate.
Finally, just to add yet another drop to this compilation of oddities that's about to overflow, you should know that lakes of Saumur have even been found at the bottom of the oceans. These form in deep abyssal depressions by the accumulation of water that has slowly dissolved the surrounding salt deposits, until they reach a salinity 8 to 10 times higher than the seawater we know.
It's still strange to think that, despite the vastness and multitude of these mountains, ranges, faults, and canyons, strangely, they contribute very little to the dynamics and to the shape of the immense conveyor belt, which, on a global scale, is capable of mixing the waters of all the oceans in just over 1,000 years.
The thermohaline circulation, which links warm equatorial surface waters to cold polar waters, is self-sustaining. The differences in temperature and salinity of water masses across the world's oceans. And so, the engine of this conveyor belt draws much of its fuel, its energy, from the icy and salty waters that sink at high latitudes.
Today, the small Atlantises that we still have to discover, the mountains yet to climb, require us to dive in order to find them. Yet, our curiosity, like our spotlights, are mostly directed towards the sky, towards the heights. Just think that in the United States, the annual budget allocated to National Aeronautics and Space Administration would be enough to fund the ocean exploration campaigns conducted by National Oceanic and Atmospheric Administration for 1,600 years. All things considered, maybe in the future we should think about pointing our rockets in both directions.